Hi, my name is Kirsten Martinez, and this is my group's project for presenting Chapter 12. Turbomachines, as defined in the textbook, are mechanical devices consisting of several blades attached to a rotor that either extract energy from a fluid, which would be classified as a turbine, or add energy to a fluid, which would be known as a pump. All of this is possible due to the result of dynamic interactions between the device and the fluid. Now, both liquids and gas can flow through a turbomachine, and whether the fluid is a liquid or a gas, the basic operating principles are the same. However, there are certain design criteria that must be considered depending on the state of the fluid. For example, for a liquid, the design consideration must consider cavitation, and for gas, the effects of compressibility must be considered. Now, there are three types of turbomachines, and they are classified based on the fluid motion as it passes through the blade. So one is axial flow, two is radial flow, and three is mixed flow. So mixed flow is a mixture of both radial and axial flows. And based on the scenario, different types of turbomachines are more advantageous and some are disadvantageous. So basically, different scenarios call for different types of turbomachines.
My name is Adam, and I'm going to go through sections 12.2 and 12.3 for the turbo machine project. So 12.2 is about the basic energy considerations, and work transfer in turbo machines can be obtained by considering operation of a household fan, which would be a pump, or a windmill, which would be the turbine. And the fluid velocity of these can be obtained by the sum of the relative velocity and the blade velocity, which would be represented by V equals W plus U, where V is the absolute velocity, W is the relative, and U is the blade. And U equals omega R in terms of angular. And in these problems, we're going to assume the fluid's perfectly guided by the blade. The fluid enters and leaves the fan at the same distance from the axis of rotation. So U1 equals U2, or the blade velocities are equal. In actual turbo machines, the entering and leaving flows will not necessarily be tangent to the blades due to outside environmental factors, and the fluid path lines are able to change radius, but we're going to ignore that. So in the pump, the blade is pushing the fluid. So if you look at this diagram here, the blade will push the fluid and the velocity vector will be tangential to the way the pump moves the fluid, because the pumps are like the blades pushing on the fluid. Think of a fan. And then in the turbine, you have the fluids pushing the blades of the fan. So think of a wind turbine, how the wind pushes on the blades of the wind turbine and turns it. And here's an illustration of that, where the fluid will be pushing on the blade and it will be turning. And then some great real world examples of turbines. Wind turbines and wind farms are used to generate electrical power all over, and they're becoming increasingly big. And there's actually current turbines in the ocean, which are being considered, where the big ocean currents are turning turbines and also generating electrical power. And since seawater is more dense than air, the power can be extracted because air is less dense, but it's faster, whereas seawater is more dense, but slower. So you can still get some great electrical power generation from that. And then section 12.3, angular momentum considerations. So when the shaft torque and rotation are in the same direction, we have a pump, like the household fan. Otherwise, we have a turbine, like the wind turbine. So this is the moment of momentum equation. The left side here, the sum of the external torques acting on the contents of the control volume. And then the right side is the net rate of flow of moment of momentum through that surface. And that's basically just think of the particles coming in through the blades and the fan, and that's what this represents. And then here we have the Euler turbo machine equation, this right here, and it's derived from the axial component of this big equation, and it's just a very popular equation used to find the torque of the shaft. And then these are some basic equations to find the shaft power for radial, mixed, or axial flow devices with compressible or incompressible flows, and these are just different ones. You could use the Euler, plug it in here, or you could just form it yourself. This is it in terms of mass. You divide the mass out. And then the same shaft work can be calculated from the speed of the blade U, the fluid speed V, and the relative speed W. So from 12.2. And then turbo machine work is related to changes in absolute, relative, and blade velocity. So they are all related. Remember, V equals U plus W. And then a great real world example of angular momentum. So automatic transmissions in cars, they use hydraulic torque converters. And currently in the US, over 84% of the cars do use these automatic transmissions. So they are very used nationally and probably worldwide. And the torque converter basically uses transmission fluid, not air, so actual fluid, and consists of a pump, which would be the fan, which is driven by the engine, and then a turbine, which is the unplugged fan connected to the input shaft of the transmission, and a stator to efficiently direct the flow between the pump and turbine. So again, that's just using this equation up here. You have this fluid coming in through the fans, and in turn, you're making a velocity, which in turn helps the automatic transmission.
Hi, my name is Kelly, and today I will be discussing section 12.4. The centrifugal pump is one of the most common radial flow turbo machines. This pump has two main components, the impeller and the volute casing. As you can see in this picture, it shows the inlet, suction, the outlet, and the impeller. And then the casing goes on the side. This is more of a simple drawing of what the pump looks like. Centrifugal pumps come in a variety of arrangements, but the basic operating principle remains the same all throughout. They are used to transport fluid by converting kinetic energy to hydrodynamic energy of the fluid flow. The flow through a pump is a complex process because of the unsteady flow and the three dimensions. However, the basic theory relates one-dimensional flow between the inlet and the outlet. Here you can see a list of equations that relate multiple variables when we're solving a problem that includes a centrifugal pump. In this case, V theta 1 and V theta 2 are the tangential components of the absolute velocity. HA right here is the actual head rise of the pump. But in this case, we have to keep in mind that this will always be less than the ideal head rise because of the loss in the pump. Equation 6 relates the overall efficiency of the process, which in this case is the power gained by the fluid divided by the shaft power driving the pump. Some of the section highlights for this part would be that on the suction side of the pump, there are a lot of low pressure points that can lead to cavitation. This should be avoided because it can cause loss of efficiency as well as a lot of structural damage to the pump itself. For a proper pump operation, we need the available net positive suction head to be greater than the required net positive suction head. And then there are multiple ways that we can arrange two pumps if that's necessary. So they could be arranged either in series or in parallel to provide for additional head of the flow capacity. If we were to arrange the pumps in series in order to get the resulting pump performance, we just have to add the head flows. But if they were arranged in parallel, then we have to add the flow rates instead. And this kind of concludes the section on centrifugal pumps.
Hi, my name is Ellifritt, and I'm going to be talking about section 12.5, dimensionless parameters and similarity laws. Some of the dependent variables spoken about in the last section is actual head rise, shaft power, and efficiency. And they can all depend on these variables here, which are stated above. And after dimensional analysis, you get this dependent pi term here, which can be turned into three dimensionless parameters, which are shown below: the head coefficient, the power coefficient, and efficiency. And within these dimensionless parameters, this last term here, which is a form of Reynolds number, can be ignored because the Reynolds number is usually high, so we can ignore that. And then this term here, which is surface roughness, can also be ignored because it is normally the geometric factor is so much more dominant that we can ignore this as well. And because we're talking about pumps that are geometrically similar, we can also ignore this first term. So then it whittles down to these equations here. And the last term inside, which I state here, is another dimensionless parameter called flow coefficient. And it's important because if two pumps of a family of geometrically similar pumps have the same flow coefficient, you can set the other dimensionless parameters equal to each other as well. So here's the flow coefficient equal to each other, and then here are the others equal to each other, these ones from above. And these are known as pump scaling laws and are used to relate geometrically similar pumps. And there are two special cases. The first special case we're interested in is how change in operating speed of a given pump will affect other pump characteristics. These equations here are obtained from 12.32, this one here. And we can assume flow coefficient is the same because we're talking about the same pump. It's just at two different speeds. So the flow coefficient is equal, therefore we can get these equations. And the other special case is when we are interested in the change in impeller diameter of geometrically similar pumps operating at a given speed. So the speed's given now, and how that affects its pump characteristics. So in this case, the flow coefficient and speed are equal. So the following equations are obtained, again, by equation 12.32, similarly to how they were above here in the first case, but you get these ones here. Another important dimensionless parameter mentioned is specific speed, which is obtained by eliminating diameter between the flow coefficient and the head coefficient, which gives you this. You can see the diameter goes away. And then this one here is the same equation. It's just this one, 14.44, is more commonly used in the US because this is given in the US customary units. And similarly to specific speed, this is another dimensionless parameter known as suction specific speed. So very similar, basically the same, just a little different. And it's obtained similarly as well. And then this is again the more commonly used equation in the US, which is not dimensionless. It is the dimensional form in United States customary units. Section 12.6 is about axial flow and mixed flow pumps. From previous sections, we know centrifugal pumps are radial flow pumps that operate best for applications that require high heads and low flow rates. When the opposite is required, low heads and high flow rates, an axial pump is commonly used. And there is a picture of the schematic for an axial flow pump. Centrifugal pumps typically yield specific speeds less than 4,000, and axial pumps typically yield speeds higher than 9,000. So when an application requires a specific speed in between those two values, there are mixed flow pumps that are used. And as you might guess, a mixed flow pump has both radial and axial components. A neat application of centrifugal and axial flow pumps, or axial flow pumps, is an LVAD pump, which is implanted alongside the heart to aid the heart's left ventricle in the continuous flow of blood throughout the body.
This is section 12.7, and I'm going to be talking about fans. So fans are most commonly used to move air or some sort of gas or vapor. In the industry, there are different fans. They can vary in size and shape and even usage. Some of them are used in common household or office items. And there are some that are used in like a larger scale processes and industries. So as you can see in the picture on my left, this one right here, you can see a larger fan. So that'll be more for like an industrial process. And then this one would be smaller, and it's considered to be a desk fan in a sense that you can use it for any daily activities. Fans can be called differently depending on the position they occupy in a system where you're using them. So if they're positioned at the entrance of the system, they're called a blower. If there's some sort of they have some sort of intermediate position that you can call them a booster, and an exhauster if they're at the exit of the system. As is in the case for pumps that we have discussed previously, fans can have radial flow, mixed flow, or even axial flow. And to describe the performance, then we can use similar equations as we did for pumps. Most equations that we use, they're going to be using the static pressure raise to describe the fan performance. So this equation right here, it's relating two different fans. You can use more depending on the system that you have. So then this case, PA would represent the fan total pressure, and the ratio of PA over the density, it just represents the speed of the fans. For centrifugal fans, they have a specific speed range that could be anywhere from 2,000 to 20,000. And then axial fans can range between 50,000 to 200,000. So the range is a little broader, but just because they have multiple usages, like I mentioned before, and in larger scale processes, the speed can vary depending on what you're using it for. And this concludes the section about fans.
Okay, so I'm going to discuss section 12.8, which is turbines. As I explained in the intro, turbines extract energy from a flowing fluid, and this is possible by the fluids exerting a torque on the rotor in the direction of its rotation, and then a resulting shaft power generated, which is available to then drive generators and other devices. Now, there are two types of turbines, one being impulse turbines and two being reaction turbines, and the main differences between the two are that in impulse turbines, the force on the blade is produced solely by turning the fluid, and in reaction turbines, it's a combination of both the fluid turning and a reaction of the acceleration of the fluid. Now, to compare turbine blades, we calculate the degree of reaction, which is the ratio of the drop in static pressure across the moving blade to the overall drop in static pressure across the fixed nozzle plus the moving blade. For example, the comparison using this calculation is that impulse turbines have an R equals 0, our degree of reaction equals 0, and for reaction turbines, it ranges from 0.1 to 0.7. A classic example of an impulse turbine is the Pelton wheel. This operates by the impulse of the jets of the fluid striking the buckets and generating a torque. The space around the Pelton wheel rotor is not completely filled with fluid, while most reaction turbines are completely filled with fluid. It has tangential flow, which means that it doesn't have axial or radial, but tangential. Also, the relative velocity magnitude of the liquid in the impulse turbine does not change. However, it changes in direction. So this change in direction results in a torque and a power output from the turbine, which is how the impulse of the jets generate the torque. Now, some relative equations in this section are turbine efficiency, which can be seen on this document. And one thing to note is that in this equation, HA is the actual head available in feet. Another equation relevant to this is the power specific speed, which is used to provide which turbine type, either axial or radial, will operate most efficiently, which can be seen here. And then there's also a dimensionless form of this power specific speed equation.